Good evening, everyone. Today I'm presenting the intelligent control of electric trucks. As we know that trucks are the backbone of the freight transportation of in the U.S. and which contribute to the major portion to the economy. But the trucks are also contributing towards greenhouse gases and the pollutions. If we go towards the stats, so yeah, transport sector contributes around 59% in the greenhouse gas emissions. So in that 29%, it in the US, and it contributes around 3% in the global emission. And in this 29%, there are 24% heavy duty and the medium duty trucks. And the importance of the trucks can determine by that the 70% of the freight is transported by the trucks. So it shows that the US needs a zero emission vehicle technology for our heavy duty trucks. So it emphasizes the importance of the electrification of our heavy duty trucks. So the electrification of the heavy duty trucks gives us huge benefits over diesel or a conventional truck. What are those benefits? It gives a 34% annual fuel cost saving. There is a 65% reduction in energy consumption. The electric vehicles can provide 2.5 times more powertrain efficiency. And if we talk about the well-to-wheel emission, there are huge reductions in gases, which include the carbon dioxide, the NOx, and the carbon monoxide. So this shows that electric trucks offer a sustainable alternative as compared to the conventional diesel truck. The effort of making the electrification of our heavy duty trucks and a zero emission vehicle technology, it is connected to a PACCAR Supertruck 3 project, which is funded by DOE, Department of Energy. The major goal, this project is very big, but one of the major goals of this project is to develop the zero emission vehicle technology and extension in the range, freight efficiency improvement. And our contribution in this project is to minimize the energy losses by the means of advanced power train controls. Because the power train controls are required for the energy efficient operations. So before we dive into the powertrain controls, it is important for us to understand the powertrain of an electric. The powertrain of an electric truck is very simplified. We have two e-axles over here. The e-axle is a combination of this inverter, traction electric machine, a heavy duty gearbox, and a differential. And they are directly coupled to the tires. And here we have the batteries, large batteries, which gives us the power to the traction electric machine and which eventually goes to the wheels. So each component in this powertrain architecture has 95% efficiency, except for traction electric machine. Traction electric machine can go up to like 70 to 95% efficiency, but it's based upon how you are operating that machine. So from this powertrain architecture, we can see that it is very important to operate this electric machine efficiently to have energy gains. And if we talk about a very well-known vehicle model, which is only an F equals to MA. This is the F, this is A, and this is M. And this is the load, the force which is acting on the wheels. This is a road load equation. The road load equation consists of, this is the air drag, this is a rolling resistance, and this is the resistance due to a road grade. We are talking about the trucks. The trucks they are started from 17,000 pounds to 82,000 pounds when they are fully loaded. So this mass is a very significant value. So in the air drag, it is the mass is not there, but in the rolling resistance, the mass is here. But you can see that it is being multiplied by a rolling resistance coefficient, which is very less than from one. So yeah, it will be like will be able to cater, but the gradient resistance, the vehicle is directly being multiplied by the gravitational acceleration and a sign of alpha. The sign goes from 0 to 1. 0 in a case if there is no road grid, only a flat surface. But this G is 9.8, so which makes it, if it is 0.5, then it can make it 5. 5 times the vehicle mass. If it is fully loaded, then it will 5 times into 82,000 pounds. So this is a very heavy force and most dominant force in the case of the gradient. So if back to this equation, so we have the top at the wheels, the wheel radius, the road load, the vehicle mass, and this is an acceleration. If we rearrange this equation for the wheels at the top, so we will get this equation, and this is the torque at the wheels. So the only source for the torque is an electric machine. So this equation will be translated into this electric traction machine. If you need this much torque at the wheels, you need this much torque at from the electric machine. And if you need this much acceleration, you need this much speed at the wheels. So from the acceleration, you are getting the value of the speed and the torque. So it shows that the acceleration is determining the operating points of your electric traction machine. If you want to drive rushly, then you will be putting more torque and extracting more speed from your motor. And if you are driving gently, if you are accelerating gently, you are not stressing out your motors. So from this, so my approach to cater this thing that an acceleration is giving me the operating points of an electric machine. So I just used a look ahead information. And from that look ahead information, I generated an optimal acceleration profile for the electric truck. From the acceleration, I can take out the value of the speed and the value of the torque, which is required. So what I want to do that if what I'm saying that we need to accelerate optimally. How we can accelerate optimally if there is an uphill, we can slow down a little bit. When if there is a downhill and the grade is negative, so we can speed up our vehicle or we can left the gas pedal so that more energy can be recovered. So for that, the optimal acceleration, I formulated an optimal control problem. The optimal control problem, this is a power, the wheels. What is the power? Power is the product of the F load into the velocity, and this is the vehicle velocity. And the power into dt, and this is the integrator, so it becomes the energy. So this first part of this cost function is an energy required at the wheels. And the second part of this cost function is your deviation from a set speed. If you want your vehicle to go at 55 miles per hour, and you also want some energy savings, so how much it can deviate from the 55 miles per hour. So in the case of uphill, you can say that, okay, the minimum I can go 50 miles per hour. So it will respect that. And this cost function, we need this cost function balance subject to the vehicle speed should be between the minimum and the maximum velocity, and the acceleration should be within maximum and a minimum acceleration. And this is a well-known equation that if you know the acceleration, how you can calculate the velocity. And this J is a cost function. We want to minimize that with respect to an acceleration. and then we will be getting our optimal velocity for the vehicle. So like how vehicle will be adapting for the road grid. So if we have this vehicle here and we have a road, so this vehicle can look ahead for a distance d, and within a distance d, there are segments, n segments, and for the n segments, within every segment, it is calculating power and the deviation from the speed. And since it is a distance-based optimization, so it is calculating the time as well. The time is the dx over v. And the dx is total look ahead horizon and how many segments you want in it. If you need 10 segments, so this each segment will be of 10 meters. Like within the 100-meter horizon, it will have 10 values to optimize. And in the end of this look ahead horizon, it calculates the energy and the total sum of the speed deviation from a set point. So for example, if this is a road grade profile, we have on a road, and this is a set speed. I said that this will be my set speed for my entire journey, and this will be the optimal velocity. What this optimal velocity is saying that when there is a zero road grade, you can go at the V set. When the road grade is getting negative, it is speeding it up because it is using the negative road grade force to accelerate, and in this case, it will be regenerating. And if it and then the road grade is increasing, so the speed is decreasing. So it is following this trend. This is just for showing that how the optimal speed will be following the trend of a road grade, and how we can minimize this cost function. There are so many techniques to minimize this cost function. If you want the global optimal system, then you can go for our dynamic programming. In this method, I use the sequential quadratic programming to to get an optimal solution for this cost function. And how that SQP algorithm works. So I'm showing the one iteration of this algorithm, how we can calculate the optimal acceleration. The very first step, compute function evaluation. So based upon, we were minimizing the cost function with respect to acceleration. So this function should be a function of an acceleration. So the cost function is given as a function of an acceleration. And there are certain constraints for that. And this is a cost function with those constraints. Constraint optimization can be translated into the unconstrained optimization by using a Lagrangian. So we took the Lagrangian over here. This is all less than inequality constraints, and this is the equality constraint. So there is no equality constraint, and there are four inequality constraints that speed should be less than V minimum, or speed should be greater than V minimum, it should be less than V max, and similarly for the acceleration, it should be within the range of the EMA and the EMAX. And the primary feasibility is if these constraints are met. So this G as a function of A should be less than or equal to 0, and H of A should be equals to 0. Then this, if these constraints are 0 and we got the value of an acceleration, so it is a feasible value of the acceleration. If any value of an acceleration is violating these feasibility, so we cannot, it is an infeasible solution. Okay, so here we got our first guess and how we can go forward for our next guess. So the next guess is here the SQP lies. So what then SQP does that it break down an optimal control problem into several control problems or quadratic problems and solve it iteratively. So how it is breaking this cost function? So this is the function up here. This is the Hessian matrix. Hessian is just the gradient of Lagrangian, and this is the y. So it is, if you give it this cost function, it will be this optimization problem to make the next guess. So this y is just a direction on an objective function and in which direction the optimal solution lies. So this y will tell us either we need to accelerate or decelerate, that direction of an acceleration. And the next step is find out the step size. How much? So from this problem, we got that how much we need to accelerate or decelerate. With from this step size, we get to know that how much we need acceleration and the deceleration. If we got the direction and then the step size, so the next guess will be a linearized value. This is a linear equation. The previous value plus the step size into direction, it will be your next value. How we can determine that if this next value is optimal? So the next value is optimal. We can check it by the first order optimality, or it is also a KKT condition that the derivative of this Lagrangian should be equal to 0. But in your coding or programming, you can set the tolerance that you are saying 10 to raise power minus 10 is 0 for you. So the tolerance you are setting here, it will be telling you about your optimality. If this value converges for a guess for an acceleration, then that value of an acceleration will be your optimal acceleration. So this is how we are calculating the optimal acceleration during one optimal acceleration routines iteration. So here we got the optimal acceleration, and here we got the results. This is the efficiency map. And on that efficiency map, we are just plotting the operating points. The conventional controller, which is just following a V set. So it is ignoring every road grade. If there is an increased road grade, so it is giving more pedal. And if there is less negative road grade, so it is braking at that point, and it is just sticking at a V set. And this optimal operating points, they are adapting the speed with respect to the road grade. And in the end, we will look how that speed profile looks like. So we can see that at this portion, the conventional operating points are going into 80% efficient region, but then optimal operating points are they are all using a 90% efficiency region. So at this point, so when we are operating that electric machine efficiently by looking ahead information and adapting the acceleration with the road grade. So with this strategy, we got energy efficiency improved by 4.76%, SOC improvement by 5%, and a time is increased. So the energy and the time, if you are emphasizing on energy, you will be increasing your time. So if you are trying to tuning one parameter, the other will be getting worse. So this is called a Pareto optimal situation. So the time is increased by 3% in the case of the optimal acceleration. So at this point, we have operated our electric machine within optimal operating points. But is there any other way to improve more efficiency of our machines? So we have two electric machines on both e-axles, and at this time we are splitting evenly. So if we need 1600 Newton meter torque, so 800, they are giving you both. So if I request a 1600 Newton meter at this speed, They both are giving me 800, and the power loss is 20% and total efficiency is 80%. Same operating with the same operating point, we want to increase the efficiency. So at this point, we are splitting the torque between two electric machines efficiently. So the same amount of the torque is requested from this algorithm. It gives 850 Newton meter from the one machine and 750 Newton meter from the other machine. So the power losses in this even split was 20%. The power loss in this split was 18.48%. And it was giving us the same power with an efficiency of 80%. And it is giving us the same power with 82% efficiency. So it shows that not only accelerating optimally will solve all our problems, but we need to allocate the torque optimally to both electric machines as well. So it depends one more step in this technique that first you have then optimal acceleration, which are the optimal operating points. You have the torque and the speed value, and then there will be a powertrain level control, which will be allocating the torque to both electric machines. So this is how the optimal torque allocation routine is working. Here we have an optimizer. The T-in is coming from the optimal acceleration part. So this ohm or omega is showing us the torque split. If we are getting 50% from this, so there will be a 50% from other one. If we are getting a 40% from here, then 60% should be from here. So total 100% torque should be allocated between both these e-axes. So how it is calculating that? It is, we have the efficiency map. So here we can calculate the loss at the machine. We have the loss at the gears. We have the loss at the differential. So if we request this much torque, this will be the T out. If we request this much torque from this e-axle, this will be the T out. And there is a summation. And from this summation, we calculate what is the total efficiency of a powertrain. And then it goes back to the optimizer. And then this optimizer minimize these losses. So this optimizer is minimizing the losses. So again, it will be an optimal control, and we need to formulate the optimal control problem for this optimizer. So this is an optimal control problem formulation for a torque allocation. This is a power requested. So the torque request and then omega request. These are the operating points coming from the optimal acceleration. These are the losses at the electric machine. These are the losses at the gears. These are the losses at the differential gears, and this is total efficiency. So the cost function says that this is an energy loss at the powertrain, and we are minimizing the energy losses at the powertrain so that we can allocate the torque optimally. So the condition in this optimal torque allocation problem is that the gear numbers on both e-axles should be same. Both e-axles should be running on the same speed. Otherwise, there will be a slip between cars. And this torque allocation ratio should be from 0 to 1, 0 to 100%. And the SOC should remain within the allowable range. So this calculates an optimal torque allocation by minimizing the cost function with respect to the losses. 1 minus efficiency is giving us the losses. So this is the cost function, and we need to minimize it. Again, we need a solver to minimize this cost function. And to minimize this cost function, again, I choose the SQP routine. This SQP routine is similar to a previous one. First step is evaluate the function. We are minimizing with respect to the torque allocation ratio. So this function should be this cost function should be a function of a torque allocation ratio. There are certain constraints. We are calculating the Lagrangian over here to make it then constraint optimization, checking a primary feasibility. The next guess is same, going about the what are the direction, what will be the step size, and after knowing the step size and the direction, from a linear approximation, we can calculate the next guess of the torque allocation. And if it fulfills the KKT condition for a first order optimality condition, so it is declared as then optimal value of a torque allocation. So from the torque allocation, so in this operating points, we give then OTES mean optimal torque even split, which was first method in which we gave them we extracted the optimal torque from the optimal acceleration, and it was an even split. And this OTOS means the optimal torque to the optimal split. So we can see that in the region part, there is this red one in both figures are not same. They are at this point, it is extracting less torque from this electric machine to save some energy. So there are some points in which we don't need the both electric machines running. We can take the torque from the first one and we can save some losses up there. So just allocating the torque, allocating the optimal torque for the electric machine, we increase the energy efficiency. So the previous one was 5 point something. So with this, we gain 0.68% more energy efficiency and more SOC increase. And there is an EM losses. The EM losses are reduced significantly. There is 6% reduction in the EM losses just to allocating the torque optimally. And when there are losses are very less on the machine, so it will be increase the machine's life. So in the first step, we calculated the optimal operating points by calculating the optimal acceleration. And in the second step, we have those optimal operating points value. We just allocate those to both e-axles optimally. So this is an overall block diagram of this scheme that from this look ahead information, it is generating an optimal torque, generating an optimal acceleration, and the integration of acceleration is the speed. And from F equals to MA, we got the force, and from the force we can extract the torque. So here's the torque. So the first step is giving us the optimal speed request and the torque request, which is an operating point. This operating point is going into the optimal torque allocation, and then it is giving this optimal torque and allocated optimally to both electric machines. And we from this electric machine, then we got the output. This output is going into the gearbox, and the gearbox output is going to the differential. And here we have the tires, which is running the front. So this is a complete block diagram of that work. I'll just show. So now we'll go to the simulation part, in which we did the simulation of this work. So we have a route from Columbus to Akron, which is a 222 kilometers route. And the look ahead horizon is 100 meters, and there are 10 segments, so that each segment is 10 meters. So the value, the vehicle has approximating the road grade value over 10 meters, and within the look ahead horizon, it has 10 values. These are the weight of the cost function. This is a gear ratio. It is a two-speed transmission. These are the rolling resistance coefficient, which is very small. This is a vehicle mass, which is 32,000 kgs. Frontal area of a truck. This is an air drag coefficient, and this is differential gear ratio. So this is a vehicle level acceleration. Uh, this road grade profile is identical on this object. So this shows that this conventional one is just going, it's just chasing the reference speed, but then optimal speed is adapting the road grade. If there is a road grade, so it is the road grade is high, so it is slowing down. If there is a negative road grade, so yep, it comes down. But based upon our tuning factor, how much deviation do we want in the speed when there is a negative road grade? So this is this is the speed profile, and this is the torque profile. Again, we have road grade profile in it, and in this road grade profile, it shows that when there is a high road grade, so higher value of the torque are requested. When there is negative values, so it is giving us a negative torque, so we can regenerate the energy. And it also shows that the optimal torque is staying within a minimum and the maximum limits of a electric machine. So with this optimal torque is not hitting the actuation limit of the electric machine. If it gives us the value which is beyond the maximum torque that a machine can provide, so it is an actuation limit value. So that cannot be fulfilled by the electric machines. So these are the overall operating points, the conventional one, and this is the operating points from the optimal torque and then optimal torque split value. So at the very beginning, it is the conventional controller is demanding the higher operating points going into the worst efficiency regions, but the optimal torque and an optimal split operating points, they are going very gently in the start. So it is not starting from the zero because of the initial condition. So before this simulation, we are saying that the vehicle is at a set speed, uh, as in your cruise control in your car. If you want to set a cruise controller, then you need to take your car first at that speed, and then you can hit the cruise controller button. So this is that initial condition, and from that initial condition, you can see that from in this point, it is not extracting torque, not taking the torque from the second EXL, but it is extracting the more torque from this EX. And if this is torque split profile throughout the journey, and it shows that it selected a zero torque split. Zero torque split means it is extracting the all torque from one electric machine, mostly because in the case of the regen, it is regenerating from a second electric machine to get more energy when the second electric machine hits the limit. So it goes to the next electric machine to regenerate the energy. And after the zero, it's selected the even split mostly. You can see that there is an even split, a 0.5 split is visible in this profile as well. And it's selected other split values as well. So this was the operating point of with the proposed traction control and a conventional traction control. So these are the results. The energy gain in the case of the optimal torque and the even split was 4.76. But in the case of the optimal torque and an optimal split, the energy gain was 5.42. So by only doing the optimal split, we gain 0.68% energy. So the time travel in the case of a conventional control, because it is just following reference speed. So this was time, but it was increased in the case of optimal torque and condition. So in the both cases, the time was increased by 3.7%, but it shows that if you are splitting the torque optimally or allocating the torque, it do not contribute in the time gain. So the time gain is the time increment is also is coming from that optimizing the acceleration. The final SOC, uh, again, the torque optimally give us a 0.5% gain in the SOC. The EM losses, they are phenomenally reduced in the case of the optimal split. And the range is extended in all cases. That for the optimal speed, optimal torque even split, it gave us almost 5.94% range. And in the case of the optimal torque and optimal split, it gives us the 7.43 range extension. So we didn't change anything in the powertrain, just from the control side. And we just maneuver the vehicle optimally and then allocate the torque optimally. We gain the extension in the range by 7.43%. And some part of the range extension is coming from the optimal splitting the torque optimally because it is reducing the EM costs. So in this part, we will check the road grade variation on our algorithm. That the road grade was changed by -10% and +10%. So to check the sensitivity, how much any parameter is sensitive to a road grade variation. For the sensitive, if the road grade is -10%, so it is 0.092% sensitive. So it shows that a 10% variation in the road grade is not producing any sensitivity for an optimal control command generation. Similarly, for the +10%, it almost the same values when it is 10% or when it is a -10% value. So here from this road grade variation, we got our results generalized that if there is a ±10% increment in the road grade, so we can get a 1% change in energy calculation, a 0.04% change in the time calculation, 1.3% change in SOC results, and 0.4% change in the EM losses, and 0.4% change in the drivetrain losses. Drivetrain losses are the gear losses and the differential losses. And the range is affected by 1.2%, with varying the road grade by +10 and -. So the conclusion of this work was the optimization of acceleration gives us a huge improvement in the range extension and the energy consumption. The torque allocation gives us some contribution in the range extension and the energy consumption minimization, and but it increases the powertrain efficiency. So the increased powertrain efficiency eventually reflect in the range extension and the energy gains. So I would like to thank my team for this work. My supervisor, Professor Dr. Kadir Ahmed, co-supervisor Dr. Athar Hanif, Dr. Manfredi is not here for this presentation, and the PECCAR for this work. Thank you, and feel free to ask me questions.
If you have any questions, okay.
For that road grade variation, does that mean like you multiply, like if it was a 10% increase, you would increase the road grade overall by 10%? Like you multiply it by 1.1?
Yes.
Okay. Just wanted to clear that out.
questions online?
What will be the next step?
So the next step is instead of using the efficiency map for the electric machines, so we will be using a dynamic model for the electric machine. The next step is to go deep in the controls of the electric machine to improve more efficiency.
Are you expecting some improvement by changing the control of electrical machine?
Yes, by improving the literature shows that there is a room for the efficiency gain with an improvement of the motors control. So the literature shows a 2% improvement in the efficiency, 2% reduction in the aging, and a 10% efficiency in overall.
It means this will be overall around 8% for the whole powertrain.
Is expected, but there are some other factors.
Let's break down this 8%. I was planning to ask the same question. So how much percentage improvement through look ahead information? How much through the split? And how much through the drive?
So when we have only optimal, the look ahead information is around 5.6. When we have optimal torque and optimal split, that is 10.43. And
Total?
Yeah, total.
No, no, I individually, I want to know individually. And then eventually these efficiencies will multiply, right? Or these gains will multiply.
Multiplying will add.
So I'm not multiplying or doing anything to the efficiency. So every time if I need to calculate the efficiency, so I'm doing it by the formula. That is.
Okay.
So now.
Because efficiencies eventually multiply, right? And then you get the total efficiency, but you are calculating in this way. Okay.
So this results, so if for the percentage wise, it shows a 0.6% gain with only optimal split. And the optimal torque are provided to boards. So and
Let's keep simple. With look ahead, how much you get?
5.42.
5.42.
Yes.
Okay. Now with optimal 4.76.
4.76 energy gains.
Right. Then with optimal split, how much you get?
5.4.
So these are the two numbers. And then you're expecting
Machine efficiency.
which is around 2%.
2%. So getting around 7.
So I think they will, when these gains are efficiency gains, efficiencies get multiplied for the overall. So 5 times 4 times 2 is 0.05 times 0.04 times 0.02. That's the overall. So this question, I think, is critical when we say, okay, each stepwise, how much are the gains? How, and eventually when you implement this or in the simulations, for sure, you will get this accumulative number. Any other question? Thank you for presenting and hope to see the next steps in coming year. Sure. Thank you.
Thank you.